Okay, thank you very much for still being here for this third lecture. Yeah, before I talk about characteristics P, I wanted to make two comments about the previous lectures. So the first comment is something that what I said yesterday I was not completely sure, and Paolo told me, gave me a reference for the result I'm about to state now. So in fact, it was proved by Halperin and Stashev. That descent of formality holds in general. I mean, the hypotheses are you need your CDGA to be finite type and connected, but certainly not simply connected for CDGAs. So this, yeah, is formality of compact Kähler manifolds. The Deligne-Griffiths-Morgan-Sullivan implies that they're actually, and this result implies that they're actually formal over Q. And the other comment I wanted to make before talking about positive characteristic, I wanted to just say a few words about, because I think it's interesting, about Hopf formality. So for instance, I gave the example of the little disks operad, or this example of the operad of moduli spaces of curves. And these operads, they're operads in topological spaces. So when I take chains, well, I have a DG operad, but the fact that they come from topological spaces tell me that I have a diagonal map, which is extra structure that I have. And maybe it's more classical when I dualize, the cohomology of a space has a cup product. And there is a notion which I learned about it in Fress's book, but maybe it was, I don't know if he introduced this definition. So there is a notion of a Hopf cooperad. So, well, I'm going to attribute this to Fress unless someone has a complaint. So Hopf cooperad is an operad in CDGAs. So the opposite category of the category of CDGAs has, it's a category with products. So a tensor product of CDGAs is the co-product in the category of CDGAs. So when I take the opposite category, it's a product. And so I can define an operad in this category. And that's what Hopf cooperad is.
By cooperad, you mean the comonoid in the category with the circle. So now,
yes. Yeah, well, I mean precisely this, an operad in this opposite category. I mean, yeah, Hopf cooperad, you should take this as just one word. Yeah, and the point is, well, so, yes. I think nothing. Yeah, it's just that. Yeah, I think nothing would go wrong. Well, I mean, that would involve dualizing something, so up to some finiteness assumptions. Yeah, the point of this is that Okay, let me continue. So now, well, you can observe that if X is a topological operad, well, you can apply a Sullivan differential form functor on X. And this object is almost. And I'm saying almost because, so of course, yeah, maybe X is not a good name for an operad, but that's fine. So it's almost a Hopf operad. So certainly for each RET you have a CDGA of operations. But the problem is this omega star PL functor. It's not, well, depending on where you put the op, it's not a lax monoidal functor. So it's not, the operatic structure is not going to be preserved on the nose. Instead, what you'll have is the circle product so it's contravariant, so it would go that way. And on the other hand, well, you'd have a way of comparing this. Where's your eraser? Here. And there is a map going the other way to omega star PL. And this map is a quasi-isomorphism by the Kunes isomorphism. So it's not quite a Hopf operad, but maybe you still have this zigzag, which you should think of as the trace of the operatic composition in X. So, sorry, oh, yes, of course. So, well, there are different ways to deal with this. And actually, Fraisse, in his book, he actually constructs a version of omega star PL, which sends operads, topological operads to Hopf operads. And which is quasi-isomorphic to the standard omega star PL. So on each space, it does something which is quasi-isomorphic to the standard omega star PL, but it has the property of sending. I mean, it's defined on the category of topological operads, and it lands in the category of Hopf operads. But maybe I want to describe a slightly different way to deal with this kind of structure. And it will be related to Marcy's first talks. The way to deal with this is to introduce infinity or, well, infinity operad tends to mean something more specific than what I'm going to say. Just infinity operads. But yeah, let me introduce a slightly more general context before specializing to operads. I'm going to introduce the notion of an algebraic theory. An algebraic theory is a small category with finite products. And an algebra for an algebraic theory over an algebraic theory T, so an algebra, sorry, in C over an algebraic theory T. So C is some other category, is a product preserving functor, finite product preserving functor from T to C. So in particular, this only makes sense when C itself has finite products. And well, this is a language that lets you encode, most algebraic structures. Well, precisely algebraic structures that can be described only like with Cartesian product, like groups, monoids, rings, etc., operads. So yeah, let's give an example. Let F group the full subcategory of groups spanned by finitely generated free groups. Then FF group op is an algebraic theory. So it's a small category. Well, let's say you take a skeleton of this, it's going to be small. And of course, if I take the co-product of two free groups on finitely many generators, I get a free group and finitely many generators. So when I pass to the opposite category, a product of this, the opposite of this category has finite products. And an algebra over T in the category of sets is just a group. So maybe a slightly less obvious, and it's actually a good exercise to understand what an algebraic theory is. So if you have a group, you can map any finitely generated free group to it, and this gives you a contravariant functor in this category of finitely generated free groups. And it turns out that this is an equivalence of categories. So any contravariant functor that preserves products is actually going to come from a group. And if you've never seen this, yeah, I think it's a good exercise. And you see that now that we have this language, we know what it means to consider groups in any category with products. We just define them to be functors from T to your category that preserve products. So for example, we've seen an example of category with products, namely, well, let's forget about the DG. And commutative algebras, op is a category with products. And you can consider groups in commutative algebras op. And that's what's usually called Hopf algebras. Yeah, any category with products. So for example, if you consider a category of differentiable manifolds, you will get Lie groups, etc., etc. Yes. Sorry. What did you say? Yes. No. No. Okay. And well, another example, which I'm not going to detail. So there is an algebraic theory for operads. So I'm just going to say it in words. You take, it's just similar to the case where you take, for groups, you all the finitely generated free groups. For operands, you consider all free operands on finitely many generators, and consider the full subcategory of operands spanned by these objects. And this has coproducts, because if you take a coproduct of two such operands, you're still in that category. And the opposite of that is the algebraic theory for operands. So a product preserving functor from these two sets is exactly going to be an operand in sets.
So it works for operands in sets.
Yes.
I have the feeling there are categories of operands in certain categories that you will not be able to.
Yeah, of course. So it works only if the symmetric model structure you use is the Cartesian product. Right. So, but so a good thing about this formalism is that it makes it clear how you weaken or homotopify such structure. So now I can make another definition. And it's very similar to what Marcy was explaining about how you can encode infinity operands in spaces or infinity cyclic or modular operands as certain functors on a category of trees, sending certain maps to weak equivalences. So let me make a definition. So let C be a so let me say it like this, a model category. I mean, it's not so important that it's a model category. All I care about is that it has a notion of weak equivalences and it has finite products. A weak, or, yeah, and let T be an algebraic theory. A weak T algebra in C is a functor from T to C such that whenever you take two objects in T, you get a map from f of s, f of s cross T to f of s cross f of T. And you require that this map is a weak equivalence. A strong T algebra, a T algebra in the previous sense, you would require that this map is an isomorphism. In that case, you just require that it's an equivalence. So yeah, this is just the map. By the universal property of products, you get such a map. Well, you have a two projection from S cross T to S and S cross T to T. So induce a map from f of s cross T to f of s and f of s cross T to f of T. And you can assemble them into a map to the product. So, well, this is, at this point, it's just a definition. It's not clear that it's interesting or useful. It turns out that in many cases, we have a strictification result that let us say that a weak T algebra in simplicial sets is the same, homotopically the same data as a strong T algebra in simplicial sets. So there are rigidification results. So the names I should cite here are Badziok and Julie Bergner. Tell you that in some cases, the homotopy category of weak T algebras in simplicial sets is equivalent to the homotopy category of T algebras. In simplicial sets. And in particular, this is true for T, the theory of groups or monoids, or T, the theory of operads. Or cyclic operads. Similarly, you can make a theory of cyclic operads, and this would be true as well. And now we can get the theorem I studied yesterday about formality of the Sullivan functor was sort of so we was flexible enough that you get a version of Hopf formality almost for free, and it works as follows. So if T, so the theorem you get. Yeah, sorry, before saying the theorem, I have to make a remark. So now I can formalize a little bit more precisely what this sort of structure is. So remark, if X from T to simplicial sets is a, so I don't even need to be a strong algebra. Yeah, there is.
Yeah.
Sorry, I think someone should just mute themselves. So if X from T to simplicial
হ্যাঁ ঢুকাই দিতে হবে
এটা এই যে এটা আছে না এটার সাথে সাটিয়ে দিতে হবে
কার সাথে
এই যে এটার সাথে
সেটা বলো তুমি চাপে দিচ্ছি
Okay, I think it's good.
লাগাতে ছিঁড়ে যাবে
দাঁত দিয়ে কামড়ে ইয়ে করে।
আমি চাপ দিতেই পারি কিন্তু ভেঙে যাওয়ার ভয় আছে রাত লাগবে না এমনি
But you repeat key pause or is it?
Okay, maybe I confused the one.
Okay, so the remark I was going to make is that if X is a, for this remark to work, you only need even to be a weak T algebra. Then this omega star PL of X is a weak T algebra in CDGA op. So, well, this is completely completely elementary. It just well, it's just the fact that even though omega star PL doesn't preserve products, it preserves them up to weak equivalents. So this statement is true. So in particular, if X is say a group in simplicial sets, so in simplicial group, then omega star PL of X is going to be weak T algebra in CDGA op. So it's some sort of homotopy coherent version of a Hopf algebra. Or if X is an operad in simplicial sets, then omega star PL of X will be a weak operad in CDGA op, something you might call a weak Hopf cooperad. So it's homotopy coherent version of this definition there. And now I can state the theorem that follows almost immediately from what I stated yesterday. So now if you have if I have a T algebra in, or even a weak T algebra, well, I guess that would not make sense. So let's say T algebra in smooth alpha pure schemes over C. So the category I had yesterday. So alpha is a rational number, a strictly positive rational number. So if I have a T algebra, then omega star PL of X is connected to cohomology of X by a zigzag of weak T algebra maps. So by what I've said yesterday, it's true if I remove the word by the zigzag of weak T algebra maps, but sorry, in CDGA. But the result I've stated yesterday would be true if I remove the word weak T algebra maps, but just saying by a zigzag of CDGAs. But in fact, being a weak T algebra is just a property for a functor from T to some target category. So since and it's a property which is stable under weak equivalences. So since each step in the zigzag is weakly equivalent to the other, so each of the map will be a map of weak T algebras. Yes. And well, you might say, yeah. Then if you don't like this, you can in the situations where we have a rigidification result, like over here. Yeah, this implies. So I'm going to state this as a slogan. The rational homotopy type of X is determined by the cohomology of X as a T algebra in graded commutative algebras. So the cohomology is actually a strict T algebra in graded commutative algebras. And this determines the rational homotopy type of X. So as a T algebra. And exactly. Yeah. And the reason for this is, well, you can connect, you can apply a Sullivan realization functor to X. So Sullivan realization functor, sorry, to omega star PL of X. So this is also going to be a weak T algebra in spaces. And this is going to be connected by a zigzag to the realization of the cohomology of X. And this, if you like, you can, in those situations, you can rigidify it to a strict T algebra. And this strict T algebra will be what you might call the rationalization of X as a T algebra. This can be rigidified if you want. And the other side as well. So in that sense, so it's a bit, I mean, in a way, I don't really know how to formalize. Well, I know how to formalize it using Fress's construction. So you could say something is formal as a topological operad is formal as a Hopf cooperad if Fress's construction applied to it is formal in the category of Hopf cooperad. So in general, I don't know how these two statements relate. Well, of course, this would be harder than this. And I expect that they should be equivalent, but I don't know that someone has written this down. But in any case, I think this is certainly sufficient for any purpose you might have. So in particular, the examples I've given of, so the example of the moduli spaces operad, it would be formal as a Hopf cooperad in that sense, just by the general result here. But also, well, this doesn't quite fit into the theorem, but the example of the little disk operad, the proof I've given is using the Grothendieck-Teichmüller action. But this Grothendieck-Teichmüller action actually existed at the space level, even at the groupoid level, this PAB model. So using this kind of ideas, you can show that it's formal as a Hopf cooperad in that sense. So I just thought there was, yeah, maybe slightly different. Yeah, this Hopf formality result is not so mysterious when you phrase it in this language, I think. Okay, so now I can go to the main topic of my lecture, which is positive characteristic. So let me erase this. Which theorem?
This theorem.
Well, this theorem is trivial. It just follows immediately from the theorem I stated yesterday.
Okay, perfect.
Yeah, the important fact is that a T algebra is just a functor from T, which satisfies a certain property. So the important fact is that it's a property, it's not extra structure, being a weak T algebra. Yes. Yeah. Yeah, for sure. Yeah. Yeah. I mean, an algebraic theory is any algebraic structure that you can. You look at the axiom, and if they only involve Cartesian products, they will be. You will be able to define them this way. Probably. Yeah, we can think about that after the talk if you want. Well, yeah, R modules you can encode. Yeah, in an abelian category, I don't know, over a ring, maybe. Okay, so let me, maybe I'll try to give a 10 minutes overview of étale cohomology in order to be able to phrase the results I'm going to state now. Okay, 10-minute course on étale cohomology. So, well, étale cohomology is a particular example of sheaf cohomology, and you've probably learned at some point in your education that so if X is a manifold, well, it holds much more generally. if X is a manifold, you can compute the singular cohomology as sheaf cohomology with values in the constant sheaf. So singular cohomology of X with coefficient in some abelian group A is isomorphic to sheaf cohomology of X with coefficient in a constant sheaf A. And in fact, this statement, this is slightly less trivial. This statement can be lifted at the level of cochains. So in fact, if R is a commutative ring, singular cochains X with coefficients in R are quasi-isomorphic to what are sheaf cohomology cochains? That's usually what people denote by our Dirac functor of gamma. Well, the problem is that, well, if you look at the standard definition, this will only be defined up to quasi-isomorphism. But you can actually find a model of this. There are models of this construction that come equipped with E-infinity algebra structures. And this will be true as E-infinity algebras. So instead of working with singular cochains, you can work with sheaf cohomology, and you get the same kind of structure that you have on singular cochains. So now what is étale cohomology? So now, so if X is a scheme over some base field K, well, you can define what étale cover is. So this is some algebra geometric definition. So an étale cover, it's a collection of maps mapping to X, which are jointly surjective, and such that each of them is étale. The étale map is an algebraic, it's an algebra geometric definition, but one way to think of it, it's like an algebra geometric version of covering space in classical homotopy theory. Well, not quite well. Maybe more accurately, a local homeomorphism rather than a covering space, but with finite fibers. But in any case, you can define, there is such a thing as étale cohomology. Étale cohomology of X with coefficients in any abelian group, and in fact in any étale sheaf on X, is by definition the cohomology. It's the sheaf cohomology with respect to this notion of sheaf with respect to étale covers. And an important result is that this is, in some cases, related to classical cohomology. So I think it's a theorem due to Artin. So if X is smooth over the complex numbers, you can relate the étale cohomology of X and the singular or sheaf cohomology of X, and they're going to be isomorphic. So gamma is global sections, and R is the Dirac functor of global sections. Yeah. So this will be an object in the Dirac category of abelian groups, and we take cohomology. So if X is smooth over C, the étale cohomology of X with coefficient in a finite, so it's important, a finite abelian group is isomorphic to the standard sheaf cohomology of the underlying topological space. Something which I'm going to denote like this: a smooth variety over C is in particular a complex manifold, so it's in particular topological space with coefficients in A. Under proof, sort of you have a middle term, which is instead of working with a standard open cover sheaf theory to compute this, you can instead work with a more general notion of sheaves, which is you say a map, a collection of maps is a cover if each of them is a local homeomorphism and the joint is surjective. It turns out instead of using the standard Gortonic topology to compute this, you can use this other version, and this other version it relates well to étale cohomology. So that's okay. That's a very nice result. But what makes this particularly nice is that this side tends to have interesting operators acting on it in some cases. So let me explain this now. Right. So now assume, so well, I'm gonna so restrict the framework a little bit. So let K be a p-adic field. So some finite extension P. So well, I can take the algebraic closure of K, and there is you can always embed this into the complex numbers. It's like it requires the axiom of choice, but there exists such embeddings. Now you can relate the étale cohomology of and let X be a smooth scheme over K. You can relate the étale cohomology of the base change of X from K to K bar with coefficients in A to the étale cohomology of the base change from K to a complex number. So K bar embeds into the complex number. And I guess the map goes the other way with coefficients in A. And this we've just said is the same as something that I'm going to denote by singular cohomology of X top with coefficients in A. So X top, by X top I mean take a base change of X to C and then take the underlying topological space. And well, it turns out that this is also an isomorphism. This is a standard theorem in étale cohomology. It's called a smooth change of base theorem. So this is somewhere in SGA4. So, right. So now, well, here we have a singular cohomology of X, so something we understand well. Yeah, and as always, A is finite. And here we have some other cohomology theory, but on this side, sort of obviously by functoriality of étale cohomology of the functor. So this has an action of the absolute Galois group of your field. So you see, if you're interested in understanding the cohomology of an algebraic variety over C, but if you can sort of descend this variety, show that it comes from a variety that is defined over some periodic field, then you get this interesting action of a Galois group on your variety. For instance, if your variety is defined over Q, over the rational, well, it's certainly defined over QP for any P, and you can do this game. Okay, so I think that's all I'm going to say about étale cohomology. Yeah, and yeah, one thing I should say that all these maps, all these isomorphisms, they lift at the cochain level. So as infinity quasi-isomorphism at the cochain level. Okay, so yeah, in general, yeah, étale cohomology in some cases gives you interesting group acting on ordinary cohomology. Yeah, you can make like this kind of statement. You can make a model for the derived global section that has an infinity algebra such that what I said is a what? Yes. Yeah, of course, yeah, yes. Yes, and maybe one thing I should say, so what happens when A is not finite? Well, yeah, there is something called the étale cohomology with coefficients in some L-adic, with L-adic coefficients. So étale cohomology with coefficients in the L-adic integers or in the L-adic the L-adic numbers. And the way it works is, so it's not quite sheaf cohomology with coefficients in the constant sheaf, in these constant sheaves. What you do is, so what is denoted étale cohomology of X with ZL coefficient is the limit over N of étale cohomology X with Z mod L to the N coefficients. And then étale cohomology of X with QL coefficients is the cohomology with ZL coefficients tensored over ZL with QL. It turns out that by sort of standard homotopy theory tools like your universal coefficient theorems and things like that, and the fact that smooth schemes have finite type cohomology, you can actually show that these cohomology theory for things that are defined over the complex numbers, these cohomology theories also coincide with singular cohomology. Étale cohomology of X with coefficients in ZL coincides with singular cohomology of X top with coefficients in ZL. Yes? You mean you really take sheaf cohomology with values in the constant sheaf? I think you get something which is very badly behaved. Well, this will compare to this, but I think they tend to be very pathological. These. cohomology groups. Okay, so, right. So now we have this technology that tells us that there are interesting Galois actions on cochains over certain spaces. The problem is that these Galois groups are quite complicated to understand. So I'm going to simplify things a little bit. So there is a map from the absolute Galois group of K bar over K to the absolute Galois group of the residue field of K. So what I denote by little k is the residue field of big K. So big K is a periodic field, so it has a periodic valuation. So you can look at the integers inside capital K. So it's that's a subring of capital K, which has a valuation, and then you can mod out. You can take the quotient by the ideal of things of strictly positive valuation, and that gives you the residue field of capital K. So for instance, for QP, QP, the ring of integers would be ZP, and then the residue field would be FP. And there is a map like this. I'm not going to explain how it works. I'm going to explain how it works. So here, if you have a finite extension of little k, you can sort of lift it at the integral level using, for instance, Witt vectors. So a finite extension of little k gives you a ring extension of the ring of integers, and then you can invert P to get a field extension of capital K. And by sort of Galois theory, this induces a map of Galois groups going the other way. So there is a map like this. It turns out that it's surjective. An absolute Galois group of finite fields is one of the few things that we can actually compute in Galois theory. So yeah, Galois K bar over K is generated. So it is isomorphic to the profinite completion of the integers and generated by what's called a Frobenius. So by the map x goes to x to the q with q the cardinality of little k, which is some power of the prime number p. So, you know, in positive characteristic, putting something to the q's power is a field. It's a ring homomorphism, and this generates the absolute Galois group of little k. Okay. So now I'm going to state a theorem. And I also have explained how to use it afterwards. So that's what we proved with Joanna in our second paper. Yeah. So I have to fix some notations. So let L be a prime number different from P. Let H be the order of Q in FL. So Q is the cardinality of my residue field, so it's some power of P. So Q will be a unit in FL, since any power of P will be prime with L. And therefore, it makes sense to talk about the order in that group. Then the functor from schemes over K, which are, sorry, one last thing I need to define. Let alpha be some rational number between 0 and h. Then the functor from smooth schemes over K that are alpha pure to chain complexes over FL given by X maps to singular chains on X top with FL coefficients. This functor is formal. Is N formal with N equals H minus 1 over alpha. And I'm going to explain in a second what N formal means. Well, I'm going to explain it right now. So meaning that there exists a zigzag of quasi-isomorphisms of max, sorry, not quasi-isomorphisms, of n quasi-isomorphisms. So let me write as follows. There's a zigzag of lax monoidal maps connecting F to homology composed with F, inducing isomorphisms in homology up to degree n. So in yesterday's lecture, I was saying that a certain functor was formal, so there was a zigzag of quasi-isomorphism of flax monoidal functor connecting your functor to its homology. Here it's similar, but you have a zigzag, but the maps are not quasi-isomorphisms all the way. They're quasi-isomorphism up to a certain degree that is given here. Yeah, big N. Up to degree capital N, sorry. And so I think in order to understand the theorem, I just need to define what I mean by an alpha pure scheme. So definition, scheme, a smooth scheme over K is called alpha pure. Again, it will be similar to what we said yesterday. if for sigma a lift of the Frobenius. So yeah, we have this map here. I've said that this group is generated by the Frobenius, so you can lift it here. And if for some lift of the Frobenius, the action of sigma on the cohomology and the étale cohomology of X is changed to K bar with the FL coefficient is given by multiplication Q to the alpha n, where n would be this number here. So it's the same convention as I had yesterday. If alpha n is not an integer, so this means that this group would be trivial if alpha n is not an integer. And if alpha n is an integer, the lift of the Frobenius acts in this way. So it's quite a complicated definition. And it's not at all clear that you can tell if a scheme is alpha pure or not. Let's see. So let me give some examples. It's actually not so bad. It's sort of similar to a kind of examples I explained yesterday. These Galois actions, they're nice enough that they're going to be compatible with most of the tools that you're used to in algebraic topology, like Maia-Viettori long exact sequence or Serre spectral sequence. And you can compute these Galois actions from sort of very basic examples. And deciding if a scheme is alpha pure is not always too hard. So that's our theorem. And I don't think I really have time to explain the proof. And in any case, the proof is very similar to the theorem I described yesterday. It's just that, so in the Hodge case, I was using the fact that any mixed Hodge structure would split. The weight filtration would split. In that case, there is a similar splitting. So in that case, you would split using this decomposition in terms of generalized eigenspace for the action of these automorphisms. But the problem is since any number in FL is a root of unity, you will not have a complete splitting. You'll have a splitting. It's not going to be a Z graded splitting. It will be like a Z mod H graded splitting. And that's what explains that you don't have formality all the way. But let me just give some examples of applications. Right. Also, I can come back to my two favorite examples. So the moduli space operad. So now I look at this operad with FL coefficients. And this is 2 times L minus 2. So it's formal up to degree, homological degree 2 times L minus 2. So the larger L is, the better the formality result is. So if L is 2, it doesn't tell us anything. And let me give another example, namely the little disk soprad. Yeah, it's that much formal even as a cyclic operad, if you want. The point is, this is an operad defined the category of smooth schemes. It's even defined over Q, so it's defined over QP for any P. And what you do is you just pick a P that has maximal order in this field. So you have a lot of choice for P, so you should be clever and pick a P that has order. So the maximal order you can have is L-1, so you pick a P that has this order, and this theorem will tell me that it's formal up to L-2 over alpha. In that case, alpha is actually 1/2, so that's what explains this number. And the other example, which doesn't quite fit into the theorem, but it's proven using the same circle of ideas. I take the little 2-disk soprad with FL coefficients. This is L-2 formal. So this is, well, now with this result of Weintraub, maybe we can prove it using this technology. The way we prove it in the paper is we just use the fact that there is this Grothendieck-Teichmüller group action that Marcy and Damien told us about. So here it's more like the profinite Grothendieck-Teichmüller that we would use. And this Grothendieck-Teichmüller group action, it comes with a cyclotomic character, so we can find an element in there that will act in such a way. And using the same kind of ideas, we can prove this. Yes.
So are these without the formality of
Sharp?
Or
yeah. So this one I'm not sure, but I assume so. I haven't made the computation, but this one is sharp. So yeah, that's a remark I was going to make. C star over D2 FL is not L-1. So this is as formal as you might hope for. And I expect it's probably true in the other example as well. Maybe Paulo knows. Yeah. So yeah, proving this remark is actually not hard using a symmetric group because this is a statement as symmetric operad. And in fact, one can show that if I look in arity L, this is not quasi-isomorphic to homology with FL coefficients as sigma L modules. So of course, chain complex over field and its homology are always quasi-isomorphic. But if I take into account the sigma L actions, these two things are not quasi-isomorphic. It's not very hard to see. This one, if I take homotopy orbits with respect to a sigma L group, this will be chains over the unordered configuration space, so it's finite dimensional. It has finite dimensional homology because it's a homology of a manifold, actually. Whereas this will have infinite dimensional homology. No, sorry, the homotopy orbits of this with respect to the sigma L group action will have infinite dimensional homology. Yeah. Yeah, I mean, this contains a summand H0, which is just FL with a trivial group action. So the homotopy orbits of this will contain as a summand the homology of the symmetric group with coefficients in FL, which is infinite dimensional. All right. I'm supposed to stop in 20 minutes, right? Yeah, so maybe, I wanted to explain another point of view on this theorem, which is due to Gabriel Drummond-Cole and myself. So maybe I'll do that now. And then I'll give a couple more examples. So maybe in the interest of time, I think I'm going to just state this theorem for associative algebra. But in fact, in the paper with Gabriel, it's a bit more general. So yeah, so another take formality using operatic calculus, actually. So this is a joint work of with Gabriel Drummond-Cole. And so what we do is prove a certain, well, let me state a lemma that we prove, which is, so we have a proof which is quite computational, so it would be good if someone could give maybe a more elegant proof. Let V be a rated module. So R will be some quantitative ring. Lambda is a unit in R, such that lambda to the n is -1 is also a unit. And suppose we have an infinity algebra structure on V, such that, I think the notation is M1, so the differential actually is 0, and Mk is 0 for k greater than or equal to 3. Sorry, no, that's not what I, sorry. Such that M1 is 0, so M2 is not 0. And Mk is 0 for k up to n plus 2. And the second piece of data we have is an infinity isomorphism. V to V, whose first component so yeah, I think the standard notation is this, whose first component, the first component of an infinity isomorphism will be an actual map from V to V. Whose first component is multiplication by lambda to the n. So if we have these two pieces of data, we can change the infinity structure to make the next operation be 0. Then there exists a different but isomorphic infinity algebra structure M prime on V such that M1 is 0 and Mk is 0 up to the next level. And an infinity iso, so maybe this one I'm going to call sigma, an infinity iso sigma prime from V to V with this new infinity structure such that, well, the diagram, sorry, VM well, this diagram commutes. Sorry, I think I forgot to say something. I want to say, yeah, there is, sorry. Yeah, I should have said, yeah, maybe I'm going to write it here. So this is actually 3. Well, the most important one is that this new infinity structure is isomorphic to the previous one. So an infinity isomorphism VM prime. And now I require that this diagram commutes. Right, so, okay, so let me repeat the punchline. I start with an infinity algebra whose first few components are 0, and I have an automorphism of this infinity algebra, which acts, well, this condition is like, it means that it acts, sorry, is multiplication by lambda to the n in degree n. So it acts in degree n by multiplication by lambda to the n. Then I can modify the infinity algebra structure and modify my automorphism so that the new infinity algebra structure has one more component, which is 0. But the condition to do that is to be able to divide by lambda to the n minus 1. And a consequence of this, using this, you can sort of prove inductively that certain infinity algebra are trivial. So here's our theorem. So let A G be a DGA. Such that the homology of A, so over R, such that the homology of A is a homotopy retract of A. So this is in order to be able to apply the homotopy transfer theorem. So for instance, if you're over a field, this is automatic. But if you're over, say, the integers, like, or over any PID, for instance, this will be true if A and H of A are both free. Um,
Just remove the ending prime and the finish now is the game.
exactly. So this is our inductive step. And now I'm going to put it into a theorem, this consequence. Yeah.
Yes, but I mean, not here. It has a specific ISO.
Mhm.
Just when you have multiplication like that, which might mean the sigma prime. So I won't say how you use it.
Sorry, yeah, I should have said this. Sigma primes still has this property. Sigma prime, first component, still the same. Thank you. Consequence. So if I have this, so lambda is a unit as before. Let sigma be an endomorphism of A such that the induced map in homological degree n is multiplication by lambda to the n. So if for all k, lambda to the k minus 1 is a sorry. So if this is a unit for all k less than or equal to n, then this pair is informal. And here, well, I have to apologize because I'm going to change my notion of being informal, but I don't know a better name for this. And I think in many cases, this coincides with my previous definition. So here, by informal, I mean in the sense that it's, i.e., it is quasi-isomorphic to an infinity algebra with zero differential and mk equals 0. For in this range. And of course, well, yeah, if lambda to the k minus 1 is always a unit, then you get full formality in the sense that your thing will be quasi-isomorphic to an infinity algebra whose higher operations are all 0. Yes?
So that's the remark. It already can, technique using characteristic 0, but I think that was hard in favor of formality. I don't know if it's a general kind of abstraction theoretical phenomenon, like
Yeah, well, I believe.
algebras or more general.
Yeah, well, that's something I'd like to know. Yeah. Yeah, I mean, the way, well, we prove this lemma. Well, Gabriel proved this lemma by writing down a formula and checking that it works. But I believe that there are other ways to get at this result. And that's certainly something I'd like to, I'd be happy to discuss. Yeah, exactly. I think it's kind of this kind of techniques might be more, might give you a more elegant proof of this. So if lambda to the k minus 1 is always a unit, then A is formal in the sense that it's quasi-isomorphic to an infinity algebra with M1 equals 0 and Mk equals 0 for k greater than or equal to 3. So when we move to this sort of operatic calculus kind of language, the better notion of formality is using this, saying that these higher operations vanish. And I mean, we discuss in the paper, like, they're very similar notions. Certainly over a field, they give the same, they give the same, they're equivalent notions. Yeah, we discussed precisely the relationship between the two notions of formality. Yeah, so this, yes. Yes, so yeah, so the way you prove this consequence from the lemma is, first step is use the homotopy transfers theorem to transfer your, well, you can transfer the infinity structure that you have on A to an infinity structure in the homology of A. Well, you have M1 is 0 at this stage. And you also transfer your endomorphism. It will induce some infinity automorphisms of that transferred structure, which is going to satisfy this condition.
You should start with n equal 1, and therefore you have the condition m3 equals.
Yeah, so I start, yeah. No, I start with n equals. So I start with a random infinity structure. I just have M1 equals 0, and the first step is to kill M3.
The lambda is m for n equals 0 minus 1.
Sorry, did I mess something up with the n? Yeah, I'm sorry. Maybe I stated this slightly incorrectly. We'd have to check in the paper. Yeah, because, well, in the paper it's sort of, yeah, I've sort of shifted the, so in the paper it's not stated for infinity algebra, it's stated for a general context where you have an operator P and a cooperator C, and so the convention, everything is shifted by 1, but I've shifted it like this to be compatible with standard notation for infinity algebra. So maybe I've made something wrong when I prepared this. So we can discuss this after the talk if you want. Yeah, so I should conclude soon. So yeah, let me just state some consequences of this theorem, like some explicit result that you can extract. Well, so I can look again at my at the examples that I had before. Yeah, so for instance, what you can show is that corollary, so let X be a complement of a hyperplane arrangement in Cn, which is defined over a periodic field K. So what I mean by this is, so remember that I've assumed that my periodic field, I've picked an embedding of my periodic field into the complex numbers. And this condition is saying that the equations defining these hyperplanes, I can choose them so that they have coefficients in this subfield K. Then I can take the cochain algebra of X with ZL coefficients. So yeah, what I like about this is actually an integral statement. It's not over FL anymore. So I think what you get in that case at this is so this, I use the same notation as I had before. Where H is the order of Q, which is a coordinate in the residue field, the order of Q in FL. Yes, in particular, sorry. One thing I can extract very easily from this is that if H is strictly greater than 1, then triple Massey products vanish in the homology of X with ZL coefficients. And yeah, I think it's very interesting because we actually know examples of complement of hyperplane arrangements where triple Massey products don't vanish. So there is an example due to Mattei. There exists for all prime number L a hyperplane arrangement, a complement of a hyperplane arrangement defined over C such that there is a non-trivial Massey product. In its cohomology, triple. So what this example shows is that, well, it shows that cohomology with FL coefficient is much more subtle than with rational coefficients, because it's known that over the rationals, all of these complement of hyperplane arrangements will have trivial massey products. But so our result shows that in some way it gives an obstruction to descending your yeah, so what we showed, what this implies that these examples of Mattei, you cannot define them over K. So there are some arithmetic obstructions to defining them over K that prevents, and so that's why our result doesn't apply in that case, because they're defined over C and they cannot be descended over K. And if you actually look at these examples, it requires the use of certain roots of unity. And if you have these roots of unity in your K, then you'll be in a situation where H is 1. So there is some subtle, well, somewhat subtle arithmetic that goes on that sort of explains how these two facts are related. And maybe let me set one last example and conclude here. Yes, definitely. One other consequence that we deduce from our result is a kind of partial conformality result in positive characteristic, or even even an integral partial conformality result for configuration spaces. So we've seen conformality in Alex Berglund's talk. So conformality in characteristic 0 is saying that a Coulomb model for your space is equivalent to the homotopy groups. And in fact, well, there is a result by Bashar that says that this is equivalent to saying that the chains on the loop space, requiring a chains on the loop space as a DGA to be equivalent to the homology of the loop space. And the Lie stuff doesn't generalize well to positive characteristic or integers, but the other thing you can certainly formulate over the integer. So my last example is conformality of configuration spaces. So a D be greater than or equal to 3. Let X be the space of configurations of points D. So again, this is ordered configurations. Then if I take chains on the loop space of X with ZL coefficients, this is L minus 2 times D minus 2. So yeah, and so this is proved using, well, this uses two ingredients. This uses my work with Pedro Boavida. To put Grothendieck-Teichmüller action in these configuration spaces. At least their P completion, maybe their L completion more accurately. So, well, when D equals 2 this is sort of classical, but we're able to extend this to higher dimensional configuration spaces. And then we use this Grothendieck-Teichmüller action as an input to apply this machinery with Gabriel. Plus the paper is Gabriel to deduce formality. So these configuration spaces, they're conformal over the rationals, and they're conformal over ZL in that sense, and up to this degree. Okay, so I think I should stop here.
Thank you very much.
Yeah, the causal dual statement is also true.
The same range.
The range.
It's associative algebra.
Yeah, I think it's the same range. Yeah, it's sort of more. Yeah, it's true. It's exactly the same technique. Yeah, so in that sense, you could say these spaces are sort of ZL causal spaces up to a certain degree in Alex Baldwin sense. Yes.
What does it mean that, like, if you have partial formality over those lines over the rational, and you give these two formality over the just
I think yes. The problem is our results, they tend to give very bad formality result over F2. Yeah, well, actually, that's something. Yeah, that's also something that operatic calculus people might be able to solve. Yes, descent of formality results. So, well, there are results over fields of characteristic 0. But I expect, yeah, in the case of infinity algebras, associative algebras, that should work over. Yeah, maybe can you descend formality from ZL to the integers localized away from L? I expect it's true, but using obstruction theory. But I never thought really hard about this. Maybe Paul knows. Yeah. Yeah. So I expect if you have formality over ZL for some prime number else, you might be able to descend for formality over the integers where you've inverted a few primes. Yeah, some kind of faithfully flat descent or something. Questions in the chat? Yes.
So we stop here.